Let's review the regions of a titration curve. So first, we have the initial rise in pH of our solution. So take note, this is the titration curve for a weak acid, strong base titration, meaning our analyte or sample solution is a weak acid and our titrant is a strong base. Initially, we observe a bit of rise in pH, followed by the slight leveling off of pH. And if we observe this leveling region, this should be the buffer region. And if we see this steep rise in pH or the inflection point, the so-called inflection point in the titration curve, the middle of that steep rise in pH is the equivalence point. And then we notice a plateau or another leveling off. This is because the pH beyond the equivalence point is dictated by the excess base in solution. Now, this titration curve that you just saw is for a monoprotic acid. That means the acid gives off one proton. Of course, we can perform titration for diprotic acids and even triprotic acids. Of course, the shape of the titration curve will be different because there are, in the case of diprotic acids, two dissociable protons, meaning we have two dissociation reactions taking place. In this case, we will observe two equivalence points. So the first equivalence point refers or is based on the first dissociation reaction, and the second equivalence point is based on the second dissociation reaction. So let's try to look at an example of a diprotic acid, carbonic acid. So the first dissociation reaction of carbonic acid is written as H2CO3 plus water forming bicarbonate plus hydronium ions. So what happens is that initially, so we have the initial pH of the carbonic acid solution. There will be a slight rise in pH followed by the buffer region for this system, which is the carbonic acid bicarbonate system. These two are the components of the buffer that displays the buffering effect in this region. As we continue to add the base, the titrant, more of the H2CO3 is being neutralized into bicarbonate until we reach the equivalence point. At the equivalence point, all of your carbonic acid are converted to bicarbonate. And now, as we add more base, we go to the second dissociation reaction. The second dissociation reaction involves bicarbonate reacting with water, forming carbonate plus hydronium ions. So there will be a slight rise in pH again, followed by the buffering or buffer region. In this case, the components of the buffer here are bicarbonate and carbonate. As we continue to add the base, more of your bicarbonate is converted to carbonate, and then we reach the second equivalence point. At the second equivalence point, all of your bicarbonate has been converted to carbonate. And beyond this second equivalence point, the pH of the solution is just dictated by the excess base. So how do we determine the pK values? It's the same for a monoprotic acid. If our basis is the first equivalence point, then we can get the pK for the first dissociation reaction. So get the volume at the first equivalence point, that's 10 ml, according to this sample titration curve. So get the half of that, that's 5 ml, project this onto your titration curve, and then project this to your y-axis. And the pH value here, that's around 2.8, that is your pK1, or the pK for the first dissociation reaction. Now for the second equivalence point, so you get your volume at the second equivalence point and get the volume halfway between the first equivalence point and the second equivalence point. So that is 15 ml. Again, project it to your titration curve and then project this to your y-axis. So that's around 7.2. This will be your pK for the second dissociation reaction.